Good day, everyone, and welcome to today's SecurityBoulevard.com webinar. We're excited that you've joined us. We've got a great topic. It's about mobile apps, securing mobile apps from the inside out. My name is Mitch Ashley, and I'll serve as your host and moderator. A few housekeeping items. We will be sending out an email to all participants with a link to the slides and also to the recording, so you can catch up on this again later. Also, we're giving away 3 Amazon gift cards at the end of the webinar, so stick around to find out who our winners are. Now, our speaker loves questions, so we love to interact with the audience, hear what your thoughts and questions are, so be sure to put those in the questions tab of the GoToWebinar software. So let's move on to our topic, securing mobile apps from the inside out. It's my great pleasure to introduce to you Eric Lafortune, who is CTO with GuardSquare. He's also co-founder of the company, and he's the creator of ProGuard. You may know ProGuard is an open source tool that's been around. Many of us, including myself, have used it for obfuscation for Java code. So Eric's got a lot of history in this subject, and I think we'll learn a lot from him today. So Eric, I'd love to have you get started. I'll hand the baton over to you and take it away.
Thank you, Mitch. Thanks. I'm happy to be here. Thank you all for joining. So in the presentation today, I will talk about the challenges and technology behind securing, hardening mobile apps. And I'll actually discuss how this is theoretically impossible. Now, if it's impossible, can it be useful at all? Let's find out. First, a few slides about ourselves. I'm the founder of GuardSquare, a software company that has offices in Leuven, over here in Belgium, and in Boston and San Francisco. But actually, our software is being used all over the world, as I'll show in the next slide, because you may indeed know us from our open source project, ProGuard. I started ProGuard in 2002. It's software that takes applications and makes them smaller, more efficient, and a bit better hardened against reverse engineering. It grew over time and became more successful, and at some point, Google picked it up and added it to its Android SDK. And as a result, millions of Android developers have now used ProGuard to improve their apps before publishing them to the Google Play Store. As a result of that open source work, we've started our company GuardSquare, and at that time we started developing other products, and the important ones of which are DexGuard, that has the same functionality of ProGuard, but focuses more and deepens the security aspect of the software, and it focuses entirely on Android. At the same time, we have iXGuard, which has the same ideas, the same goals for iOS apps. So from the list of attendees, I've noticed that you have very diverse backgrounds, and I try to cater for everyone a little bit at least, and I'll start by introducing the threats that we see in the mobile world, in our work, and then I'll go into some solutions, first at a very high level, and then going into some more technical details. So I hope there's something for every one of you. First of all, the app architecture. Mobile apps are developed, they're uploaded to the App Store, the Apple App Store, or the Google Play Store, and then end users download them to their devices. And there, these apps can run by themselves, self-contained, or more often than not, these apps still interact with services that run in the cloud and that provide additional functionality or additional storage. So there may be something of value inside the apps. There may be something of value in the data that these apps manipulate. There may be something of value in the cloud. So an attacker, a criminal attacker, will typically go after the most valuable parts that he sees in the app, and oftentimes that's information in the cloud. personal information, maybe financial information. And the way to attack that would be to attack the APIs with which the app communicates with the services. Now, this is not all that trivial because these servers are heavily guarded by anything from firewalls to complete AI systems, and the communication with an app is typically encrypted, and there may be security tokens involved. So that isn't that easy by itself, even if there are security holes in the APIs, in the interfaces with the service. So an attacker might want to do some reconnaissance first and look at the communication between the app and the services to figure out what protocols are being used, what encryption is being used, and how all of this could be potentially abused. Now, that man in the middle, such a man in the middle attack isn't trivial either. So it's targeting maybe a small group of people, or maybe just the device that the attacker, he or himself or herself has. But still, there might be typically encryption, and if the application is written properly, there is also SSL pinning that makes sure that all the communication goes to the intended servers and not to some random server in a far away country. So then the attacker may shift his or her attention to the app itself. And the first step would be for the attacker to take his or her mobile device and connect a computer to it, and then direct attacks from there. Now, there are a couple of approaches there, typically two categories. There is dynamic analysis, where the app is running on the device itself or perhaps in an emulator, and from the computer, the attacker can guide attacks on the device. He or she will do this by subverting the operating system, so rooting or jailbreaking the operating system, and then installing hooking software like Frida, for instance, that's commonly available, commonly used, to first perform some reconnaissance, find out what the data flow is inside the app perhaps, and then perhaps even tamper with the functioning of the app by hooking into it and changing the functionality on the fly dynamically. Now, by itself, this is relatively harmless still, because this is just affecting the attacker's own device. But this is just the first step for further attacks to perhaps attack other components in the system, or perhaps extract valuable information. Next to the dynamic analysis, there is a static analysis, where the app is extracted from the mobile device and installed on the computer, where it's completely harmless, completely defenseless, and can be dissected at the attacker's mercy. For this, the attacker can use traditional disassemblers or decompilers, or more sophisticated tools that can perform more advanced analyses of the application. Once the attacker has gained knowledge about the functioning of the app, he or she can actually also start tampering with the application by injecting code or by removing code from the application. For example, SSL pinning can easily be removed, and then the app can be reinstalled on the device, and that enables the man in the middle attack that the attacker wanted to achieve earlier on. So again, the static analysis and the dynamic analysis and the tampering are steps for further attacks, even if there is seemingly nothing of value inside the application. Something we see most commonly is that the app is analyzed and then tampered with, and then so modified, and the modified version, the cloned version, is uploaded again to a Play Store, either the regular Play Store, the regular App Store, or a third-party store. And there are actually two scenarios here. One in which the attacker has modified the functionality of the application For example, disabling license checks or enabling free in-app purchases or installing game cheats, things that some users might actually want and download knowingly and install and use knowingly. There is another scenario where the inserted functionality is actually malware, and the attacker just aims to misguide end users to download and install the app and use the app, and then have the malware do its work. So that's the typical use cases that we see, the typical attack models that we see with cloned apps. There's another scenario where a malicious app is uploaded and an unsuspecting user downloads and applies it, and the app actually attacks other apps on the device. So the attacking app itself may be a clone or something with a seductive title or functionality, but once installed on the device, it starts attacking other popular apps, for instance, injecting advertisements, as happened with the Agent Smith malware not too long ago. So all of this is to show that, on the one hand, the app may contain valuable information by itself, but it can also be a gateway to further attacks on the data on the device, on the cloud services, on other apps. So all of this combined with the fact that the apps are quite harmless. They are completely at the end of the software chain. They can be downloaded easily. They can be dissected easily. So as a quick overview, what kind of abuse do we see? On the one hand, there is malware or other stuff that can be injected into the app, and this is something where a publisher would like to protect the end users because such apps affect the end user negatively and indirectly also the publisher. And on the other hand, there are things that could be removed from the app, like license checks, in-app purchases, advertisements, as happened with many apps in the Google Play Store. And this is something the publisher would like to defend against, just to defend his own assets. At a higher level, what are the threats? So what we most typically see is the cloning of apps in the context of piracy, and perhaps less common, but with a higher impact, financial fraud if it involves financial apps, banking apps. The consequences, they're the same for all cybersecurity, I guess. Directly, there might be revenue loss, in the case of advertisements, for instance, but more often than not for high-profile customers, it's a matter of reputational damage, where a customer might lose confidence, trust in an application, and as a result might lose trust in the provider, in the company. And something that's becoming more important in Europe with the GDPR is also fines and retributions, where the GDPR requires that an application is constructed securely from day one. So if a developer neglects this, he can be fined seriously, as happened to, for instance, British Airways in Europe already. So what are the solutions to this? It's a difficult problem, and the solution is not all that simple. It's a matter of having layers of protection that protect the application and also one another. And I'll go into some more detail, gradually getting to more technical details near the end. First of all, a good series of guidelines is provided by the OWASP project. They have their guidelines, their standards, and their tests. And the foundation of all of this is to have a secure architecture, where you want to make sure that you have the proper cryptography, the proper authentication, and so on in place in your design. The next step, of course, is to implement that design properly and to make sure that you don't make mistakes, you don't use outdated libraries that have security holes, and so on. And then the next step on top of that, the final step, is to harden your application against the reverse engineering and tampering that I've been talking about. So this hardening, it won't solve any problems that you have at lower layers, just like the secure implementation won't solve problems that you have in your architecture, but at least it can mitigate any issues that might be there, and it can protect against the issues that I've discussed just a minute ago. In these layers of protection, we distinguish about 3 categories, starting with application integrity. First of all, the publisher wants to make sure when he or she deploys an application, publishes an application, that application is installed and run on the end user's device, that is actually the same application. And for that, there are standard techniques like certificate checking, which is essentially boiling down to checking secure hashes of the application or maybe of individual files to make sure that it's the intended application that is running. So this is something that makes the application self-defending. It checks itself at runtime to make sure that it's not a cloned version that has undesirable functionality inside of it. Now, that isn't sufficient, as we've seen a moment ago. Not only the application has to be the same, the platform on which it's running has to be untampered with as well. So if the platform is subverted, the operating system, then the application can't function properly either. The traditional way to check that is to apply root detection here to make sure that the device isn't rooted or jailbroken. But this is a bit controversial because a rooted device is not necessarily an indication of bad intent. So more suitable techniques, more targeted techniques are probably hook detection to make sure to let the app detect and make sure that it's not being attacked by hooking frameworks like Frida, for instance, or more basic debuggers or emulator environments. And finally, there's the more overall goal of raising the bar against reverse engineering and tampering. And this is both static and dynamic reverse engineering and static and dynamic tampering. And this is typically the realm of obfuscation techniques, where tools take the code and make it intentionally more difficult to interpret. And I'll go into some details in the next slides here on a number of techniques, just to give you a flavor of what happens there and how powerful, how strong this can be, or how weak it sometimes can be. So I'll talk about application processing, and this is something that ProGuard does. If you've used it before, it takes a mobile app, processes it, hardens it, and spits out a hardened mobile app that can be then uploaded to the Google Play Store or the Apple App Store. And I'll talk about ProGuard and DexGuard, and they typically provide these 3 steps. They apply shrinking, they apply optimization, and they apply obfuscation. And I'll go into a little bit more detail about these different steps. Shrinking is a process where that might be compared to tree shaking. You take a tree by its trunk, shake it firmly, and all of the dead material comes flying out. Now you can do exactly the same thing with a mobile application. You can let a tool analyze it, figure out which parts of the code and the resources, resource files, asset files are actually needed in the application, and which parts can be discarded. And this doesn't seem very security related, but actually it is at a certain point, because a lot of that unused functionality is debugging code, testing code, logging code, and maybe functionality that isn't enabled in this version of the app yet. And in those cases, it really makes sense to remove all of that code, to remove all of the information that could guide an attacker in his or her reverse engineering efforts. The second step that our tools typically apply is the optimization step. And this is like an optimizing compiler, and it's quite technical. It performs inlining, constant propagation, and so on. But most relevant perhaps in this context, in the context of security, is that the optimization step can remove logging code. Logging code is typically woven inside the application, and the optimization step can figure that out and remove that logging code again from the application. And that can be from your own code, which is of course easier to control, but that can also be from external libraries, which are much more difficult to control because you typically don't have the source code for that. And then the third step, most relevant in this context, is the obfuscation step, and the step in which detection code is injected into the application. And this is a series of obfuscation techniques, more or less applicable or efficient, effective. And I'll just try to give you a flavor there of what they typically do and mean. First of all, the most known obfuscation technique is name obfuscation. Imagine that you have a piece of code as shown on the left-hand side here, where this is just a piece of Java code where the names of the class and the fields and the methods give a clear indication as to the purpose of that code. And that can guide an attacker in the attacks, figuring out first what the code is doing before actually tampering with it. And I'm showing source code here, but the compiled code contains exactly the same information. And what the obfuscation step now does, the name obfuscation step, is take these meaningful identifiers and replace them by meaningless identifiers without changing the semantics of the code. Now, this makes it a bit more difficult for a human, at least, to interpret the code. It, of course, doesn't protect you from automated tools that don't care about readable names or not. So decompilers, disassemblers, more advanced tools, they don't care about these names at all. The next step in protection would be string encryption, where your code typically contains lots of strings, and they might be fairly harmless messages or something. They might be API keys, or they might be URLs, something that's more sensitive, not exactly top secret, but something that you might not want to show to curious eyes. And the solution there is to encrypt these strings so that they can be decrypted again at runtime. So you can imagine that this is an approach that only helps against static attacks, where with a quick inspection, the strings become invisible. But if you look at the code dynamically while it's executing, the strings, of course, become visible again. They are decrypted and then used in memory. So it has its weaknesses, but it's the next step in hardening the application. Another technique in the Java world, at least, is reflection, where a simple statement, as shown on the left-hand side, can be replaced by a construct, as shown on the right-hand side. And to a human, and even for automated analysis, this is much more difficult to interpret, or a little bit more difficult, especially if you start combining it with techniques like string encryption that I've shown before. So that can really make it more difficult to find the flow in the application between different classes and fields and methods. Another traditional technique is control flow obfuscation, where on the left-hand side you can see a series of statements or maybe blocks of instructions, and the arrows in between are branches that direct control from one block to another. Now, a human and even a decompiler will look at some patterns in these branches to figure out what the code is doing. And the typical approach is to apply a tool that changes this quite readable flow and turns the code into something more like spaghetti code that is much more difficult to interpret. Now, there are advanced tools that try to reverse this process, but it typically requires some human intervention and some ingenuity and some time. Another traditional technique is opaque predicates, where a simple constant, Boolean constant like true or false, can be replaced by something that is more convoluted. So this is equivalent at runtime, and it has a little bit of overhead, but it's way more difficult to analyze, especially automatically, by tools that try to find the flow inside an application. Similarly, for arithmetic expressions, for example, a simple sum, as shown on the left-hand side here, you can replace that by an equivalent expression, as shown on the right-hand here. And it's not immediately obvious, but this is exactly equivalent. Again, it's slightly less efficient, but it's more difficult to interpret, more difficult to read, especially if you start doing this multiple times and then combining that again with other techniques. Even though this is quite a simple approach, it turns out to have a high complexity to revert this automatically with automated tools. Just to give you an impression of what all of this amounts to, I've taken a small piece of code from an open source project. It's probably not readable in detail, but that doesn't matter here. It's just about the structure. It's a class of Java source code. Now, if you compile this Java source code to Java bytecode and then apply a decompiler to it, as we've done here with two different decompilers, one on the left-hand side, one on the right-hand side, you can see then that the code is recovered completely. So this is just, again, an illustration of how easy it is to recover the code from mobile apps, because all of the information is essentially still there. The documentation may be gone, but all of the original names and structure, they're all still there. Now, if you apply some of the techniques that I've shown a moment ago, this becomes way more difficult for these decompilers. As you can see, the decompiler on the left-hand side makes a complete mess of it. And at this point, the output is actually useless for a human to use. The code also doesn't compile anymore, so it's impossible to tamper with this result. The decompiler on the right-hand side, you probably can't read that, has given up completely. It just says that it can't decompile this code. Then there are obfuscation steps that try to take this a step further by making the code completely invisible. And the traditional approach here would be to apply encryption to the code, where that encryption is done at build time, and the code is decrypted again at runtime before it's executed. So this makes it more difficult for tools like disassemblers and decompilers and other automated analysis tools, because the attacker first has to lift the decrypted code from the application with some effort, and then can work further with that. Somewhat more advanced approach there is to apply code virtualization, where the original code, which is in the case of Android is Dalvik bytecode, that is running on the Android device, which has a Dalvik interpreter. Well, that code can be converted into an alternative bytecode, which has its own interpreter, so an alternative virtual machine. And that combination, the virtual machine plus the alternative bytecode, is shipped inside the application, and it has the same functionality, except that if an attacker wants to reverse engineer this code, it becomes a lot more difficult because he or she will first have to make sense of the instruction set that this bytecode has, and only then he or she can start interpreting what the application is doing and then maybe even tamper with it. There are advanced analysis tools that attack such virtual machines, but they have their limits as well. If you start combining this or applying it multiple times, then there is certainly human intervention and time required to get to the bottom of the original code. So that brings me to the conclusion of my presentation, I guess. So yes, theoretically, it's impossible to protect mobile apps. They're completely vulnerable. They're completely at the mercy of whoever downloads them and tries to peek inside of them. But there are lots of practical possibilities to harden the application against reverse engineering. And at this point, it's just a matter of raising the bar from something that is trivially simple to something that is actually quite difficult. And as I've tried to show, it's quite useful also. Even in the smallest app nowadays, there is something of value, something that's worth it to be protected, from protocols to advertisements to other information. And in the end, it's all a matter of economics, both for the publisher and for the attacker. For the publisher, it's a small investment to apply a protection tool to harden the application that probably offsets the risks that the publisher has. And for the attacker, it's a matter of economics, seeing if it's worthwhile to actually investigate a hardened app and spending time on it and then having uncertain rewards for it, or maybe spending time on a neighboring app that isn't protected at all. So that's the end of my presentation. Thank you for your attention. You're of course welcome to visit our website where we have some related blogs and information about our software. But Mitch, I think at this point we have time for questions.
Wonderful. Good. We've got some great questions lined up here. So first question, I think probably many of us are wondering is there sufficient awareness about the threats against mobile applications? And I guess I've kind of asked two parts, both for developers, are they aware? Are also kind of development managers, others in the organization as aware?
Yeah. I guess this is true for all cybersecurity. No, there is not a sufficient awareness. For many apps, it's a luxury. Developers are under a lot of stress to deliver, and actually making the app secure doesn't have much visibility. It doesn't have many rewards, so that's usually left as an afterthought. That's something we experience a lot. And then there are a number of scenarios that we encounter commonly. First, the app goes to an external penetration testing team, and they come back with feedback that the app has to be hardened. And then these developers become customers of ours. There's the advantage that we have is that it doesn't need to go into the architecture, something that you have to decide very early on in the development process. It's also not that much the implementation, which is a bit more difficult to change, but it's something that you can apply at the very end in your development chain. So we have a slight advantage there. That makes it a bit easier. And then I was talking about scenarios. Another scenario that we come across now and then is that in a country, a banking app gets hacked, and all of a sudden, all of the banks of that country become customers of ours. So that's also something that happens typically even in these high-profile cases. So sufficient awareness, no, but with mobile apps becoming the first priority for companies and the first priority for hackers, I think this is something that will improve over time, just like it improved over time with web apps.
Okay, great, great. We have a number of questions about obfuscation. So one kind of line of questions is about, with obfuscation, what steps would an attacker take to reverse the obfuscation in order to better understand the app?
Yeah. Let's see. It depends on the sophistication of the protection inside the app. So it's typically an iterative approach where an attacker starts using the standard tools to look at the application. In the Android world, there's a very functional open source project, APK tool. You apply it to an app and you can just read the source code of the application and the resources, and you can tamper with it, and then you can reconstruct your cloned app. So this is all very trivial. Sometimes that's not sufficient if there is protection inside the app, and then you would gradually apply more sophisticated tools. There are some standard tools here, but the most sophisticated hackers build their own tools on the fly as they go when they attack well-protected apps. So there's no single path here. It's oftentimes a matter of a lot of experience, years of trying and learning.
Okay, great. Also on obfuscation, is there much of a application performance impact or size of code impact? Of course, developers on mobile apps are always under lots of pressure to keep code size small, the runtime execution small.
Yeah. There is some impact. I've noted that a couple of times where you replace something that's very simple by something that's more convoluted. So it's in a sense, it's the opposite of optimization. The good thing, of course, with ProGuard and DexGuard is that they perform optimization to begin with. And then that process is way, way more important than any of the overhead in size or even in performance that you introduce by applying your protection. So typically it's not a problem, but we try to keep this under control also by keeping it configurable, because you can, of course, try to protect every single instruction in your application, and that would be overkill, and it would also kill the performance of your application. So generally, it's a matter of finding a balance. It's an engineering exercise. It's a matter of trying sometimes and coming to a balance between protection and overhead in performance and size. But typically, it's not a problem.
Okay, very good. Let's see, next question. You mentioned ProGuard and DexGuard. How do you know when you need which one?
Well, if you're not considering security at all, then ProGuard would be sufficient. But for any app nowadays, there is something of value inside of it. And then the basic name obfuscation that I mentioned that ProGuard applies, as I've shown, that isn't sufficient at all for any of the regular tools that are available. So you can still disassemble and decompile your application after it has been processed by ProGuard. So at this point, we consider ProGuard an optimization tool, and it's DexGuard that actually focuses on this protection aspect. And this is an arms race, really. So we have to work continuously to stay up to date with what happens in the reverse engineering world, where new techniques are being developed and we have to keep up, or vice versa. So this is an arms race, really.
It is. Seems like all of security is a bit of that, isn't it? Talk a little bit about thin client situations or thin apps where most of the logic is located in the cloud or the back end. Does the app still need to be protected? All the same methods apply? What would you do in those situations? Yeah,
at first sight, it wouldn't seem that important because the server is like a fortress and everything is well protected. But as I've discussed a couple of times, The app is also a gateway to further attacks. So it contains typically useful information about, for instance, protocols, how the app communicates with the server. And if you can reverse engineer those protocols, you can start further attacks. Also, that might be a way to create unauthorized apps that replace the original thin client and that provide different functionality, perhaps. That's something that the publisher typically doesn't want because it dilutes his brand. Another place where this could be important to harden, or where it is important to harden thin clients, is this use case or this attack scenario where other apps attack the app on the device. And this can also happen to a thin client. And then that thin client might leak information or might be tampered with by malicious software on the device. And that's where it also makes sense to harden the thin client.
Okay, great. Next question is how do distribution stores like Google Play protect customers? I think a general question is, you know, Apple and others have very stringent requirements, maybe less so in terms of Google Play, I don't know, but doesn't it help with some of the application security issues?
Yeah, so Apple and Google, they try to protect the end users from malicious apps. So they scan these apps. Google has an automated process. Apple has a partly automated, partly manual process, and they're more thorough and more strict about it. But they face the same problems, of course. And they try to protect end users. But it's actually also the publisher that needs to be protected sometimes for all of the valuable information that they have in their application. And that is something that Google and Apple aren't that much concerned with. They are concerned with malicious apps, but they're not concerned with piracy perhaps, or extraction of assets, or attacks on external services. And that's where it makes sense to harden the apps.
Great, makes sense too. Just a side question, do the app stores also concern themselves with privacy of customer information, or is that really the responsibility of the app?
Let me think. To some extent. I think Google has started scanning on a number of things, but it's mostly in the hands of the developers, mostly the responsibility, and then there's a legal responsibility also to protect the privacy of the end users. So as far as I know,
your answer. I thought that might be your answer.
Yeah, it's these are difficult things to verify. So yeah, to automate that is not always possible. It's also something that is theoretically impossible, and they just do the best they can.
Mm-hmm. Okay, great. Talk a little bit about adding runtime protection. When is that needed? Do you always need to add that? Is that good enough? You don't need to do obfuscation or some of the other techniques. How does runtime protection fit into the picture?
They are really complementary. So I haven't talked about it that much, but it's important to have both of them at the same time, because they will protect the code, the application, but they're also necessary to protect one another. If you have an application that is protected by root detection, but you don't have static protection on top of that, I've shown that it's very easy to lift that root detection and then continue as if nothing happened. So you really need a combination of both, where the dynamic protection protects the static protection and vice versa. So for us, that's very important always.
Okay, perfect. What are the key differences between the Android and the iOS platforms in terms of ad security? This is, I assume, about your product.
Yeah. So the The stores are somewhat different, as we just mentioned. The Apple App Store is a bit more critical about apps that are published and has better protection of end users, maybe as a result. So it's more of a closed garden, and in that sense, end users are more secure. But other than that, the technology is very different, but the problems are the same. The problems for publishers, for developers of apps are the same. You have the same possibilities on both platforms. You can root or jailbreak both. You can extract apps, analyze them. You have similar tools, sometimes the same tools. You can apply dynamic analysis of apps on both platforms. You can run apps in emulators on both platforms. So from that perspective, there is no difference other than that. The technology and the jargon might be different in both worlds.
Great. By the way, one of our participants loved your explanation on obfuscation, so I think we'll take another question on that. Do you need to obfuscate the entire code base? How do you decide what parts of your code that need protection? What are strategies around that?
The more, the better, definitely. It doesn't make sense to just obfuscate one name. That's something you can feel intuitively, and it doesn't make sense to obfuscate two names and so on. So the more you can obfuscate, it's like having more layers of obfuscation. You want to obfuscate more of your application as well. You want to create a bigger haystack to hide the valuable needles in there. And this is something that is true. For instance, it's something that we often get as questions for ProGuard and DexGuard, that developers are using third-party libraries, and these libraries aren't obfuscated. And ProGuard and DexGuard can obfuscate those libraries, but it seems easier to just leave them alone and just focus on your own code. But to get better results, it's definitely a lot better if you can obfuscate those libraries as well. After all, a lot of functionality will flow through, a lot of data will flow through those libraries as well, if they are, for instance, creating communication with other parts of the architecture, or if they are serializing data like JSON serialization. That's places where you really want to make sure that all of the application is obfuscated, not just parts that you would deem worthwhile protection.
Very good. Of course, one thing developers are very concerned about, given the pressures they're under, is time and things that take extra time in the development process. What does it take to set up your products, and what, can you automate how they're used in the dev process, or does it take extra time? What impact does it have on the dev cycle?
You of course need to set it up in your build process. In the Android world, this is easy because so many developers are already using ProGuard, and for our commercial product, that's just a simple step up. Our commercial product DexGuard is backward compatible, so it works in the same way. It has the same philosophy, so it's mostly a matter of just replacing ProGuard by DexGuard, and it will work in exactly the same way. Similar for iXGuard, it has some setup that you need to do. There is a bit of configuration, but once you have that setup, that also works in your build process, in your continuous integration. So there is mostly a bit of startup overhead investment, but once it's running, it's pretty smooth from there.
Okay, great. Great questions from our audience too. Here is another one. What about cross-platform applications? How do you support them?
Yeah, that's again different technology, but the same problems. So cross-platforms, that's typically with JavaScript code with various platforms like React Native, Cordova, and The language is different. It's JavaScript instead of Java bytecode or instead of native code, but the problems are exactly the same. Of course, we have to keep up with the technology. We just have to follow wherever developers are going. So we have our products for Android and iOS, and inside of them, we have support for JavaScript and cross-platform development as well. So on the inside, the technology is quite different. On the outside, the goals and the approach is quite the same.
Okay, great. Looks like we have one more question. So if the audience has any others, be sure and get those into the question tab. Last question we have right now, it's a product-specific question. ProGuard and more recently R8 are widely used to obfuscate applications. Do they provide sufficient protection? How do they compare to commercial app protection solutions?
I've touched up on that in one of the answers. So R8 is the combination of ProGuard and D8, so it combines the functionality of ProGuard and D8 in a single compiler, which technically makes sense to make things more efficient. But just like ProGuard, it just applies name obfuscation. And as I've mentioned, this is just the very basic protection that you can apply to code. It's hardly serious compared to the other obfuscation steps that are really needed to protect the code and protect one another. It's a matter of stacking layers upon layers of protection and then keeping up in that arms race. Mm-hmm. So that's the difference between ProGuard R8 and other commercial offerings or more advanced software.
Great. Actually, I'm going to throw in just a question I have, if I can, Eric. When
Sure.
I began using ProGuard, actually our interest at that time was protecting IP, intellectual property, with Java applications. Is that still a big use for obfuscation today?
Yeah, it is. But there are different angles to it. So it depends on the kind of IP, on how effective it is. So if it's something small, like maybe an API key, then that becomes way more difficult to protect than when you have a complete algorithm that you want to keep secret inside the code. So the smaller the thing that you want to hide, the easier it is generally to extract it from the application again. So there is a whole range of things that you might want to protect in the application, and protection can be increasingly effective the more you want to protect inside there. Let's see, are mobile applications any different from, say, the early midlets or applets that we had many years ago? I think what is different now, what I've mentioned a couple of times, is the protocols, and that's also a form of IP. The protocols to communicate with servers, that's something that's becoming way more important to protect, because it's a vulnerability, typically something that you want to harden.
Mm-hmm. Makes a lot of sense. Thanks for the update. So I'd like to thank all our audience for all the great questions. Of course, Eric, for your fantastic answers and insights. Just a reminder that we will send out an email to all the participants with a link to the webinar recording and also the slides. You can, of course, get those on securityboulevard.com also. Remember to check out the Security Boulevard site for any upcoming webinars, and also check out SecureGuard site, our sponsor of today's webinar. We'd also like to announce who our winners are for the 3 Amazon gift cards. And those folks are Martin C., Scott K., and Erica V. We will be in contact with you about how to get those gift cards. So congratulations to our winners. I'd like to have you join me in thanking our wonderful speaker for today, Eric LaFortune, CTO with GuardSquare. also co-founder of the company and of course creator of ProGuard. And we'd like to thank you, our participants, our audience, for joining us. We know your time is extremely valuable and we're honored that you spent it with us today. It's been my pleasure to host today's webinar. Have a great day and be careful out there.